All right, I'm going to work two derivative limits problems here, um, or limit derivatives, derivative limits, whatever. Okay, here's a function. We're simply going to find the derivative. I'm not going to do anything fancy like find the slope at a point or write the equation of a tangent line or anything like that. Just straight up find the derivative. And for the sake of shortening the video, I've pre-done some of it. This is your general definition of a derivative, or one of the two limit definitions of derivatives, and usually I will default to this technique, the limit as h approaches 0 method. And when you plug in f of x plus h and f of x, this is what you end up with. That's what you end up with, where the f of x plus h is done in blue and the f of x is in green down there. Now the challenge is, can you simplify this to clean it up and cancel that h to make the limit workable, where you can finally plug in the 0 for h? And to do that, we're going to start by distributing that negative in the numerator. So x plus h plus 3 over x plus h. Distribute that negative, x minus 3 over x. That's all over h. And then you'll notice the x's cancel, cancel, cancel. And now I'm down to h plus 3 over x plus h minus 3 over x. Well, that's the numerator anyway. All of that over h. Okay. Now I need to cancel or clean up these fractions. And I've got a lot of fractions here. I generally don't like having fractions within fractions. So what I'm going to do to simplify this is I'm going to look at every one of my terms. And what I mean by terms, I have an h, a 3 over x plus h, and a 3 over x in the numerator, and then I only have an h in the denominator. And of those four terms, out of those four terms, I find the common denominator. I have h over 1, x plus h, x, and a denominator of 1. The common denominator for those four is x times x plus h. So what I'm going to do is I'm going to multiply through the top and the bottom that common denominator, x times x plus h. And in bottom, I'm going to multiply by x times x plus h. And when you multiply that through, I'm going to multiply it by the h, by the 3 over x plus h, and by the 3 over x. And when you do that, you get a lot of simplifying. First one, not a whole lot happens. So it's just going to be xh times x plus h. But when you multiply by those fractions, this first one, the x plus h, is going to cancel that x plus h, leaving you with only plus a 3x. And on the next one, I have minus 3 over x times that stuff. The x's cancel, leaving 3 times x plus h. And I am not going to distribute or expand my denominator. I'm going to leave that as simply x h times x plus h. And now we're going to simplify the numerator, distribute the xh. So it'll be x squared h plus xh squared. Then I have 3x, distribute the negative 3, all over xh times x plus h. And I'm not going to multiply out the bottom. And now I should be at the point where I can clean up and simplify some of this stuff in the numerator. Let's see. Not a whole lot happens. I can cancel the 3x's, and I'm left with x squared h plus xh squared minus 3h. And finally, in the numerator, I can factor out an h, which will cancel with the h in the denominator. All right, so factor out that h. I resize this thing, give me some room to work. That gives me x squared plus xh minus 3 all over x plus h. And then finally, I can cancel out an h from numerator and denominator, and that's what we're trying to do. And if we go all the way back up to when we started this limit, we are trying to do this limit as h approaches 0. And as h approaches 0, so I plug in 0, so this is the limit as h is approaching 0. And then I plug that in, and I have x squared plus x times 0 minus 3 over x times x plus 0, or just x squared minus 3 all over x squared. And so that would be your answer for the derivative to this one. Quite a lengthy problem, very heavy on the algebra, but you have to be very careful with that to make sure that you don't make any mistakes. And if you really want, you don't have to do this, but this does simplify. X squared over x squared is 1 minus 3 over x squared. You could split up that fraction and clean it up to 1 minus 3 over x squared if you so desire, but that's not necessary. Or that. Okay, next problem. So let's see, that was kind of a lengthy one. The next one is just a polynomial, x cubed minus 3x plus 7. I'm actually going to show you how to do this one both ways with the h approaches 0 using this method. The limit as h approaches 0, f of x plus h minus f of x. Here is what you get when you plug in f of x plus h and f of x. The blue is the f of x plus h, and the green is the f of x. And the problem with this method, the h approaches 0 method, is that sometimes expanding the x plus h can be quite cumbersome. Something cubed isn't too bad, but the next step, you can see how long that gets. And you have to be extremely careful with your work. We still have the minus f of x on the end. And when we distribute that negative, what ends up happening is we have a negative x cubed plus a 3x minus a 7, and we can cancel a lot of stuff. Everything without an h should cancel, and it did. And if you keep looking at how this thing works out, after canceling, I had 3x squared plus h plus 3x h squared plus h cubed minus 3h. Factor out an h. Then you can plug in your 0 after you factor out the h, and you get a derivative of 3x squared minus 3, which, if you know your derivative shortcuts, the power rule, that's very easy and quick to do. But for now, I do want you to answer these with limits. But that is one way of doing this with 3x with the h approaches 0 method. I want to show you how to do the general derivative with the other technique, the limit as x approaches a technique. Now this will give my derivative in terms of a, not x. So if my derivative is 3x squared minus 3, which is what we got down here, then the answer to this one will be 3a squared minus 3. So we kind of know where we're going with it. So I'll plug in my f of x, and I'll plug in my f of a. F of x is just your function f of a, just replace the x's with a. And then I want to show you how we are going to simplify this. It's a little bit unique in how we solve this, but I do believe it's a little bit easier. So we have f of x, f of a, color-coded. I will start by distributing my negative. And so my first parentheses, the blue stuff doesn't change, x cubed minus 3x plus 7 minus a cubed plus 3a minus a 7. And you don't get as much cancelage here. You don't get as much, but the 7's do cancel. The 7's do cancel. And that would leave us with x cubed minus 3x minus a cubed plus 3a, all divided by x minus a. Now this will factor and cancel, and you can actually factor this with grouping. You would have to rearrange the terms a little bit, but I'm going to show you another way, and I've shown this before, but if I need to simplify these, if you're dividing by a simple x minus a, if we're doing the derivative of a polynomial, then you can always clean this up with synthetic division. So I wanted to show you how to do this with synthetic division, and I'm going to do that over here. So I'm going to use synthetic division to simplify it, and you just have to be very careful because you have to remember that x is the variable, and in this term a is a constant, or in this limit. And I know that because it's the limit as x approaches a. X is the variable. We are approaching the constant a. And the reason that's important is because when you set up your synthetic division, it's x minus a on bottom, so I'll set a positive a on the side, on the outside. And then I have a 1x cubed, a no x squared, a negative 3x, and then all of this remaining stuff is the constant. That is a number. The negative a cubed plus 3a, that is a constant. So that is going to be my last term to go into my synthetic division. Negative a cubed plus 3a. And I know that looks scary, but it's actually going to clean up quite nice. So we'll bring down the 1. 1 times a, or a times a, wait, what am I doing? Bring down the 1. Here we go. A times 1 is A. A plus 0 is A. A times A is A squared, and here's where you have to be a little bit careful. Negative 3 plus A squared is simply A squared minus 3. Then I need to distribute my A through that. A times A is A cubed. A times negative 3 is negative 3A. And if you do it correctly, you will get a 0 remainder. If you do not get a 0 remainder, you messed up. Now what you have to remember is that A is a constant and X is my variable. So what I'm left with is this end constant of an A squared minus 3. It's A times X and then an X squared plus that. So after you do the synthetic division, this thing cleans up to X squared plus AX plus, and then I have A squared minus 3 for my constant. Now that I've cleaned it up, I can go back up here. This is the limit as X approaches A, and when I plug in A, I will get A squared. Remember, we're plugging A in for the X. A times A is another A squared minus 3, and A squared plus A squared plus A squared is 3A squared minus 3, and that is your derivative in terms of A. That synthetic division where you have A's in it can be a little bit tricky, but I think I prefer this work with the X approaches A as opposed to having to expand out something to the third power. And the higher the exponents, the more I prefer this method. If it were X to the fourth, well then I think this is much easier than having to expand X plus H to the fourth power. That's just my opinion. You're free to do whatever you want, but I wanted to show you these two examples of finding derivatives. And that's it.